Hello. First of all, I hope one are healthy. Welcome again. I am Zeynep. I am a physics student in METÜ. At the preparation stage of this Astrobiology Live Presentation series, I was in the academics team to find academics for the event. For the second session, I will be your moderator. In this session, Janusz Petkowski will be here for his presentation called Venusian phosphine, a wow signal in chemistry. Janusz Petkowski is a research scientist in MIT and interested in finding life on exoplanets, biosignature gases, and theoretical biochemistry. Please ask your questions from the chat box throughout the presentation, because afterwards there will be a Q&A session. And now we can continue with the last presentation of Astrobiology Live Presentation series with Janusz Petkowski and his presentation. Sir, how are you?
Hello, thank you very much. I mean, this is a fantastic opportunity to speak here, and I would like to thank you, Zeynep, and thank you to other organizers, because I hope that the audience and everybody in this and every attendant of this conference is going to enjoy the lecture. And I also look forward to our discussion afterwards. And because what I'm going to talk about today is something of a very, very unexpected discovery. And if confirmed, it might have a very, very profound implications. Because what we are going to talk about today is a discovery of Venusian phosphine, which is a gas, a certain very special gas in a very unexpected place. But before we actually dive deep into the clouds of Venus, our neighboring planet, we have to actually know a little bit more about the planet itself. Venus is often called our sister planet, but it is essentially maybe a little bit of an exaggeration. It might be similar to Earth, maybe in the form of maybe because of the similar mass or similar size, but the many other environmental conditions that are actually present on this planet are actually quite significantly different than what we can find here on Earth. First of all, the planet is very hot. I mean, on the surface temperatures are extremely hot. They reach 465 degrees Celsius, which is much uh, than any environment, than any regular environment, so to speak, on Earth. We also have a situation when the planet is actually, where Venus is actually completely covered with clouds. On Earth, we have a spotty cloud cover, and Venus is actually completely covered with clouds, and that's why you cannot really see the surface that easily without any special instrumentation. But that's not the only differences and similarities of the planet. If we look at the actual atmosphere of Venus, the Venusian atmosphere is much different than what we have here on Earth. It's actually composed mostly of carbon dioxide and nitrogen, while, of course, atmosphere of Earth is mostly nitrogen and oxygen. What is also quite important, quite interesting about the atmosphere of the planet is that it has this mysterious, very interesting cloud cover, as I mentioned, and it is actually composed mostly of sulfuric acid. And it is present at the height that is called at the height of approximately from 48 to maybe 70 kilometers from the surface, and it is composed from rather unexpectedly, what we can say, from concentrated sulfuric acid. So these clouds of Venus are not made from water droplets as clouds are made here on Earth, but rather from a substance that, from the point of view of our sort of habitability of a planet, is something that's very not really favorable for life. So we have this temperate zone, and we call it a temperate zone only because the temperatures, it happens that the temperatures on this cloud layer level are actually quite mild. They reach from approximately 80 degrees to 100 degrees at the bottom of the cloud layer to maybe 0 or maybe up to -10 in the top layers of the cloud. So this is an environment. So the Venusian atmosphere is somewhat complex, and it's also quite chemically interesting. And recently we've added a new potential mystery to the long list of Venusian mysteries that were known before, because we've discovered or at least a hint of a very unusual gas in the clouds of Venus. We discovered phosphine in these clouds. And what actually is phosphine? So phosphine is a gas that doesn't really reach the headlines very often. People do not really know what it is, but it is nevertheless a very important chemical. It is the simplest gas that contains phosphorus. So it has one phosphorus atom and three hydrogen atoms. So it has an overall chemical formula of pH 3, and it is an important industrial product on Earth, and also most importantly, maybe for the rest, from the point of view of the rest of this talk, on Earth, phosphine is actually a biosignature gas. And what it means is that it's actually an exclusive product of biology. It is produced only by life, and there are no other efficient processes on Earth that could produce it. So on Earth, phosphine is only produced by life that actually lives and survives and thrives in the completely oxygen-free environments, like, for example, marshlands, swamps, or even guts of mammals or other animals inside of their intestines, for example. And of course, phosphine is also a product of human industry. It is an important reagent in various processes, and is also quite toxic to oxygen-dependent organisms, which means that it also has a quite significant importance in the agriculture industry, when it is often used as a pesticide. So you now probably understand why it is such an unbelievably unexpected discovery, or something that we didn't completely foreseen or expected to discover this gas in the clouds of our neighboring planet. And the initial discovery, the discovery of phosphine on Venus, was done by Professor Jane Greaves from the University of Cardiff, using two different telescopes. One is JCMT in Hawaii, one is ALMA. And what Professor Jane Greaves was able to actually discover is a single absorption line in the millimeter wavelength of the spectrum, with two telescopes, both with JCMT and ALMA as well. And what is actually quite interesting is that also, if these observations are correct, then phosphine's distribution in the atmosphere is also not even. So it is not evenly distributed in the atmosphere. It is mostly present in this cloud layer of Venus, as I mentioned, in the atmosphere, in the clouds, at the height of approximately 55 kilometers. So right in the middle of this temperate zone. Of course, the temperate zone in this case only means the temperature range that is rather relatively mild. The abundance of this gas is somewhat uncertain, but of course, it reaches levels of approximately 20 parts per billion, or maybe few parts per billion, in the parts per billion range, nevertheless. So this is actually quite of an unexpected discovery, because as we will learn throughout this lecture, we would not expect this gas to be present in the Venusian environment, and we would not expect this gas to be actually there. So it has to have some sort of, if this discovery is essentially, if indeed the phosphine is detected, is there in the clouds of Venus, then something interesting has to happen that leads to its production. But as it is often with such unexpected and high-level discoveries, potentially with high implications, you have to ask yourself a question: is the detection really real? It is of course the first detection of this type of this gas on the rocky planet besides Earth. So you have to ask yourself: is this really a robust detection? And we believe so. First of all, phosphine line absorption has been seen with two independent facilities, with two telescopes, so both by JCMT and ALMA. We were able to actually do these measurements, and the phosphine line measurements are also consistent under valid and independent processing methods, which is also quite important. And if you overlap the spectra from the two facilities, actually, we can also see these features, that those features also overlap, which is quite important. Now, as the spectroscopists in our team, mostly Professor Jane Greaves and also Clara Sousa Silva, also ruled out all other known reasonable candidate molecules for this signal. You might ask a question, okay, if the signal is true, let's assume that it is true, then you can ask a follow-up question: is this really the signal comes from phosphine, and maybe some other molecule is actually responsible for it. And spectroscopists in our team were able to actually rule out all the known reasonable candidates, including sulfur dioxide, which is one of the most strong contenders for this signal as well. And also, we have detected and expected as a control, as a control of the robustness of the detection, we have also detected an absorption line of the deuterated water in the right abundance and with the same procedures as well. So this is sort of a control of the observation. But of course, since the initial detection or the discovery was published on the 14th of September, the archive repository of preprints exploded with various papers that are trying to address this discovery from different perspectives. And people often claim, and some people claim, that the abundance of phosphine that was initially detected is actually different could be different from the abundance that was initially claimed. Some people claim that there is no signal at all. Some people claim that the signal actually is there, but can be explained by the sulfur dioxide instead of phosphine. We do not necessarily agree with those conclusions, and now currently Professor Jane Greaves is in the process of preparing a paper that is actually going to address that. But what is quite interesting also is that some people, like Professor Rakesh Mogul from California, had a very interesting idea. He decided that maybe it is actually quite interesting to look at data that were collected 40 years ago by various probes, and in this case, and look if maybe the analysis of this data missed some interesting information, maybe even missed phosphine signal altogether. So what Professor Rakesh Mogul actually did is that he looked at the data that were collected 40 years by the NASA probe Pioneer 13. And NASA probe Pioneer 13 was actually able to dive into the clouds of Venus and essentially check their chemical composition. It carried these little probes that were actually diving into the clouds of Venus, contained various instrumentation, and one of the instruments that was on board was actually the neutral gas mass spectrometer. And what this neutral gas mass spectrometer was able to do is was able to actually detect and identify various gases that were present in the atmosphere in the clouds of Venus. And the reanalysis of this data by Professor Rakesh Mogul actually suggests that indeed there are some ions. There are ions containing phosphorus detected in the mass spectrum from the neutral gas mass spectrometer that could actually be a signature of phosphine, and especially this phosphorus ion that was detected in this spectra in the clouds of Venus is quite interesting, because it cannot be at least not for now. It cannot be explained by any other neutral gas but phosphine. So it is actually quite possible. Of course, this is not an absolute proof, but it is actually quite possible that NASA found phosphine 40 years ago in the clouds of Venus with the Pioneer 13 probe, but didn't really realize it until this legacy old data were reanalyzed again. So this is also one other moral of this story, is that we should never discard the old data. If something is actually because some other discoveries can be made just by looking at the data with the so-called modern eye. But of course, the discussion what this phosphine really means, or is it really there, or is it really phosphine or something, is probably going to go for a while, because we have to be aware that, for example, the detection of methane on Mars is still ambiguous and debated 15 years after its initial detection. And this is despite the fact that Mars is actually much more intensively studied than Venus. It has multiple orbiters, it has multiple in situ measurements, various rovers visited the planet, and so our capability of various detections of trace gases on Mars is actually much more efficient. And nevertheless, the discussion about the Martian methane continues 15 years after the initial discussion, and it is quite likely that the discussion about the phosphine detection is not going to die out anytime soon, and it's not going to be also resolved anytime soon. This is just the very beginning of the journey, and because the next step of the journey is essentially asking what process could make phosphine on Venus. Because if we assume that indeed the discovery, the observations of Professor Jane Greaves are correct and true, then we have to ask a question: what process makes phosphine on Venus? And that's actually a seriously difficult question, because on a rocky planet like Earth or Venus, the phosphorus compounds in general are more likely to be present in this oxidized form. So phosphorus likes to bind to oxygen, so there has to be some sort of process that actually makes this transition to this phosphorus being bound to hydrogen. And this is actually quite difficult reaction. This is a reaction of reduction of phosphorus in this case, and it's quite difficult to perform in a regular environment of a rocky planet. This type of reactions, the phosphine formation, is quite readily, it happens quite readily on at least two other planets in our solar system, on Jupiter and Saturn. But those planets are very different than a regular rocky planet like Earth or Venus. The phosphine is produced deep inside of the atmospheres of those planets because essentially three conditions are met. One, there is very high temperature down in the lower levels of the atmosphere, lower layers of the atmosphere. So there is very high pressure, and also there is very high amount of hydrogen. So the formation of phosphine is actually quite favorable. The similar process cannot be really responsible for the formation of phosphine on rocky planets like Venus on Earth, because the temperatures, the pressures, and also the abundance of hydrogen doesn't make this process favorable. Moreover, we have to be aware that phosphine is a reactive gas. It is not a gas that once produced can sort of linger in the atmosphere for very long time. It's actually very readily destroyed by light, in photochemical processes, and it also reacts away with various components of the atmospheres, not only with other gaseous components, but also with, for example, some atmospheric radicals. And you do not have to really follow these graphs in detail, but it's just to show that indeed for phosphine to actually be there in the clouds of Venus or in the atmosphere of Venus, there has to be some sort of process that constantly replenishes it, because otherwise it would just react away and wouldn't be there at all. So that is sort of a mysterious conundrum that we had to actually tackle with. Then we tried to find processes that could, in principle, produce phosphine in a Venusian environment in an efficient way, to explain the detected parts per billion abundances in the atmosphere, and also to find various processes that could really that could make it efficiently to actually counteract the problem of its destruction in the atmosphere. So we looked, for example, if photochemistry, for example, if reactions with light in the atmosphere destroy phosphine, so maybe there are actually some other photochemical processes that could produce phosphine. And we realized that it is actually quite, at least, known photochemical processes, and this is actually a very, very important caveat, that we don't know everything about the atmosphere or the planet or Venus or Venus in general. So we only talk about some known photochemical processes or known chemical processes that could produce it. There might be some unknown processes that produce it, of course. But in general, if you look at this very, very complicated graph, there are always some bottlenecks in these photochemical pathways, and mostly the problem is the destruction of the phosphorus-oxygen double bond, which is very difficult to achieve, and really the photochemical processes, at least the known ones, cannot really produce phosphine efficiently. We also looked at various chemical processes that could happen in the atmosphere or in between various atmospheric species, or various surface minerals, or even minerals that are transported as dust into the atmosphere, and then essentially react and maybe as a result produce phosphine. And this is a sort of a summary graph that shows various hundreds of possible reactions and various thousands, if I'm not mistaken, of various conditions. Then none of them actually appear to result in reactions that would be favorable for phosphine to actually be produced. Moreover, we also explored whether phosphine can be produced indirectly, and what it means that, for example, you can have certain reactions that lead to certain precursor molecules, like, for example, the phosphorus acid, that could then, for example, spontaneously decompose under the high temperatures in the, for example, lower levels of the atmosphere, and then as a result indirectly produce phosphine. And those reactions also do not really efficiently produce phosphine. In this particular case, this reaction is not favorable because of the water scarcity in the lower atmosphere of the planet. Actually makes this reaction very, very unfavorable to happen. So if these regular chemical processes, regular from the point of view of the atmosphere, of the conditions on Venus, cannot really efficiently, favorably produce phosphine, then maybe there are some other processes, like some physical processes, geological processes that could produce it. So we looked at various chemical processes that could happen underneath the surface of the planet, and we realized that this also is not the favorable explanation. The mantle and the crust and the mantle of the planet is essentially too oxidized to produce phosphine efficiently. So, for example, the production of phosphine by volcanoes is simply not efficient enough. So, if at all, it will produce only trace amounts of this gas. That would be not enough to explain these detected amounts. We could imagine that there are some very, very, very special rare minerals that could happen to be more common maybe on Venus, like phosphites, for example. And this is just an example of a phosphite. We do not claim that this is actually common on Venus or anywhere else. This is copper phosphite in this case, but this type of metal phosphites could, in principle, hydrolyze and produce phosphine as a process in a process, and as a result, maybe be responsible for the detection of phosphine. But we realized that if indeed volcanoes would be responsible for the formation of for the production of phosphine, you would need actually 200 times of the volcanic activity than we have here on Earth, and unusually high water-rich mantle water-rich mantle to explain it. So volcanoes are a very unlikely source of phosphine. So we are searching further. We are trying to find some other processes, geological processes that could maybe make it. So we looked, okay, maybe there are some tectonic movements. Of course, Venus doesn't have plate tectonics. It actually did. What if we actually missed it? Maybe there are some tectonic shears and tribochemical processes that could produce it. And that also doesn't appear to work. So we then, for example, looked at lightning. There is some evidence. People claim that lightning might be there or might not be there. So we look at various lightning production possibilities. And because in laboratory conditions, for example, there might be some traces of phosphine in certain conditions produced. But this looks like also not a favorable possibility, because only trace amounts of phosphine are produced, if any phosphine at all. So even if lightning is present on Venus, this cannot be responsible for the production of this gas. Finally, okay, so Venusian clouds are really quite unusual. I mean, they contain these concentrated sulfuric acid droplets. So maybe this very weird environment somehow creates favorable conditions for the formation of phosphine, and maybe the cloud droplets, for example, participate in some reactions that could lead to this formation. And this is actually quite unlikely as well, because sulfuric acid is actually destroying phosphine or removing it instead of producing it. It's actually a very well-known fact for at least a century, maybe even more, that sulfuric acid in industrial processes is actually used to remove phosphine quite efficiently from various other industrial processes. So it is actually another conundrum that at least in the lower clouds of Venus, it is highly quite unlikely for phosphine to be produced in that way. And if at all, it's actually a very nice way of removing it from the atmosphere, in addition to all the other processes of removal that I mentioned. So if we cannot really find any obvious production pathway for phosphine on Venus on a planet, then maybe actually we can deliver phosphine or phosphine precursors from outside. So, for example, what if these favorite phosphite minerals that we mentioned when we talked about volcanoes were actually delivered with meteorites to the planet, and if they actually fell apart, if they actually hydrolyzed, maybe they could release phosphine. And that's of course a possibility, but this is not enough to actually explain the amount of phosphine that was detected in the Venusian atmosphere. Comets, similarly, it is actually there are no signs of recent comet hitting Venus, and there's no comets as a source of this phosphine discovery are also quite unlikely. And we even looked at various very, very speculative, very exotic possibilities for production of phosphine, like solar winds, for example, and none of those energetic particles reach the cloud layer, so they cannot really be responsible for the production of phosphine. So we looked at all those various processes, and we really went through it thoroughly, and we published a paper, which is available on arXiv, and it's essentially a big laundry list of various processes that actually were ruled out. So we were able to rule out a lot of different various chemical and physical processes, and this actually brings us here, because it brings us to a point that we essentially really do not know what makes phosphine of Venus. So if the initial discovery of Professor Jane Greaves holds, and indeed phosphine is there in the clouds of Venus, then we do not really know what process is responsible for its formation. And this is also because we welcome any kind of feedback from the community. If you have your idea for how phosphine can be made on Venus, or if you have some process that you think that we've missed or didn't address, you are welcome to contact me at any time, and we can have and let us know, because we really would like phosphine efficiently with insufficient amounts on a rocky planet like Venus, because this brings us to rather peculiar implications. If indeed phosphine is produced abiotically or in any other way on Venus, then of course our understanding of rocky planets is severely lacking, because this means that the rocky planets like Earth or Venus or other planets are actually capable of much more sophisticated chemistry than we previously thought. It might even be likely that there is some unknown chemistry, like photochemistry or some geology or some other atmospheric process that we simply have no idea about. And that's very much possible. I mean, the atmosphere of Venus is not fully understood, and the environment is actually quite unique. But there is also there is also another hypothesis, and it's of course rather speculative. But by analogy with Earth, on Earth, we have to remind ourselves that on Earth, there is no geological or other process or other chemical process that is responsible for phosphine production apart from life. So maybe, and this is of course highly speculative topic, but we shouldn't be ashamed to actually give this hypothesis forward, or at least discuss it. Maybe by analogy, there is a reason for the production of phosphine on Venus is actually some biological process. So is it even possible? Well, technically, of course, it is possible in a way. It's favorable in a sense that we have a precedent for the formation of phosphine by life here on Earth. So life here on Earth is capable of actually moving this reaction from actually is capable of reducing the oxidized phosphorus species to phosphine. But we have to ask ourselves a much more serious question. Is it even physically possible to produce phosphine on Venus by biology, or biologically produce phosphine on Venus in the clouds? Because we have to be aware that the clouds of Venus are, ecologically speaking, very, very different environment than any environment that is uninhabited by life here on Earth. So we cannot just say that we are just taking life from our planet and transferring it to the clouds of Venus and actually claiming or hoping that it will survive there and thrive, because this environment is ecologically so different that our life would be incapable of surviving there. And we will actually dive into this problem quite in detail, but it can be visualized very easily or very simply by this very simple chemical reaction. If you add sulfuric acid to sugar, and sulfuric acid is essentially the liquid, the main liquid, the composition. This is the substance from which the droplets in the clouds are made of. And sugar is sort of a proxy of our own biochemistry. Yes, it's sugars are one of the main building blocks of biochemistry of every organism here on Earth. And you add this sulfuric acid to sugar, and you essentially smash it and destroy it to pieces in less than a minute. So it is quite impossible for our biochemistry to be simply transferred to this environment and just expect it to survive and thrive. Moreover, from the point of view of our own life here on Earth, the environmental challenges for life in the Venusian clouds are absolutely great. They are not only focusing on this concentrated sulfuric acid environment, which is actually many, many times more acidic than even the most acidic places on Earth. In the concentrated sulfuric acid in the clouds of Venus is approximately 70% solution of sulfuric acid, or maybe or in the top clouds 85% on average, and reaches 100% at the bottom of the clouds. The highest concentration of sulfuric acid that is present, for example, in some unusual environment here on Earth, for example, the Dalol pools in Ethiopia, or the environment in the iron mountains in California, it's approximately 5%. So we have a situation when this concentrated sulfuric acid is indeed many, many times more acidic. This environment is many, many more times more acidic than even the most acidic places on Earth. So even the most hardy acidophile here on Earth would not really easily survive in the clouds of Venus, and this is only one challenge for life that we have to face. There might be also a very high energy requirements, but this is not really the biggest challenge. If we assume that life is present hypothetically in the clouds of Venus, then it of course from the evolutionary standpoint, it is a no-brainer, so to speak, to actually develop or evolve photosynthesis. So these high energy requirements might be actually mitigated to a degree by employment of photosynthesis. But there might be some other challenges for life as well, like, for example, nutrient scarcity. We have to be aware that if this life hypothetically lives only in the clouds of Venus, only in these various belts, areas in the clouds, then some of the nutrients that it would have to get are, of course, less volatile. How life copes with the fact that some of the nutrients, like metals, for example, might be actually extremely scarce in this environment. We don't know. This might be an analogous situation to a degree, analogous, of course, not the same, but analogous to the situation that our life faces when it lives in the environment of lower oceanic crust, when the nutrient scarcity is unbelievable challenge. And our life actually copes with that through various ingenious adaptations like metabolic plasticity, so it essentially can take whatever nutrient is around. It can also recycle and reuse many of the critical nutrients as well. So in principle, life could evolve and cope with this challenge quite nicely. But there are other challenges that might be actually that are quite difficult to envision how they could be actually overcome. And this is very low water content, for example. Venusian clouds are extremely dry. They are 50 times drier, at least 50 times drier than the Atacama Desert, one of the driest places on Earth. So if indeed life on Venus is water-based, then it has to have adaptations that have no precedent here on Earth. That life on Earth simply never had to adapt to environments that are so dry. So if indeed life in the clouds of Venus exists and it's water-based, then it has adaptations to that environment that we've never seen here on Earth. And we possibly cannot even predict or imagine. And finally, and this is also a challenge, we have to be aware that if life exists in the clouds of Venus, then it has to be a strictly aerial biosphere with no direct contact with the surface. There is, of course, a precedent and a very rich biosphere in our own water clouds on Earth, and life that lives in our own clouds has various ingenious evolutionary adaptations that allow it to survive in the cloud environment. But there is one catch here. Our life, and this is the Earth situation, is present on the panel on the top. Our life, even if it lives in the cloud droplets or outside in the atmosphere, this microbial life always is intimately connected to the surface and to the habitable surface of our planet. So the life cycle of these various microbes that inhabit our clouds is always connected, always related, always dependent on the fact that they are eventually deposited on the habitable surface of the planet, and they actually there divide and thrive, and then they are essentially using clouds only to survive. They only adapt there to survive, or maybe survive the transport to a new habitat, but they do not actively divide in the clouds. If life on Venus if life on Venus even exists, then it would have to solve this problem as well and have this life cycle perpetually happening only in the cloud layers, in this temperate zone, in the cloud decks of Venus. Is it possible? We don't know that. So where does it bring us? We know that if indeed, so all these challenges taken together give us one sort of view, that if indeed something lives hypothetically in the clouds of Venus, then it has to be life as we don't know it. Because there are so many different adaptations that such life would have to have that they do not have precedent here on Earth. Even if, for example, life on Venus is water-based, then it would have to have adaptations that we are not seeing here on Earth. And there might be even more speculative possibilities, like, for example, the fact that maybe life adapted even to a degree that it uses is sulfuric acid to much greater degree than we actually expect, and maybe uses it to a degree as its own solvent. This is, of course, highly speculative possibility, but we could in principle also think about this this interesting scenario. But we have to be aware that our discovery of phosphine is only one of the mysteries of Venus. It's only an additional, the newest mystery of this planet that we added to a much larger list of mysteries that were already known. Because, for example, if the modeling of Professor Michael Way is correct, then Venus might have had a very surface water, oceans, rivers, and seas, and all kinds of bodies of water on the surface of the planet for billions of years. And this is denoted by this by this blue bar here. So surface water could have existed for billions of years, until as late as 700 million years ago, when some geological catastrophe happened and the planet actually changed to the hell that we see today. So you might actually ask yourself, you might ask a question: what if life existed on Venus early on and throughout these billions of years when it was actually quite habitable and clement, and then found a way to adapt to a changing environment and escaped onto the only place on the planet that the temperatures are actually favorable for complex chemistry, to the clouds, and eventually adapted to this changing environment, and now lives there, completely changed from what it used to be in the very beginning of the planet. We have to be aware that, of course, Venus is still geologically active, as it is shown by this red bar here. So it might be that, the conditions are hostile, but maybe life actually was able to somehow adapt to those changing environments over millions and millions of years. We don't know that. And finally, we know that there are other mysteries in the clouds of Venus, in the atmosphere of Venus, that we cannot explain, besides phosphine. So if the phosphine discovery is correct, then it adds just additional mystery to a long list of mysteries, as I mentioned. Because one of the mysteries of Venus that we cannot explain for decades now is the existence of the so-called unknown mysterious UV absorber in the clouds of Venus, which is present in the form of these black streaks in the clouds. And this mysterious absorber is we don't know what it is, but it is extremely dynamic. It changes with time, with space. It changes with seasons, and we have no idea what it is. People claimed that it might be some sort of sulfur compounds in the clouds of Venus that are responsible for it, but nothing seems to fit. And there were rather speculative papers, of course, that suggested that this might be a sign of some pigment that is actually responsible for photosynthesis of some microbial life in the clouds. Of course, this is a highly speculative possibility, but nevertheless, it was put forward a couple of years ago. So where does it leave us? We don't know if phosphine discovery is correct, then we don't know what process is responsible for its production. We cannot rule out life as its source, but of course we cannot a priori favor this hypothesis of life, and not mention any other possibilities, like, for example, unknown photochemistry or unknown atmospheric chemistries, because we do not know everything about Venus. We do not know everything about the planet, so there might be some other processes that are responsible for it. So, nevertheless, we need some more aggressive investigation of the chemical environment of the clouds of Venus and the atmosphere, and we hope to actually achieve that soon, because the Breakthrough Initiatives is now sponsoring an MIT-led study of a mission to Venus to search for signs of life and even signs of life, and even life itself. We would like to actually have a mission that will look at the chemical composition of the clouds of Venus, and then essentially see if, for example, we can find some complex organics in the clouds, if we can find some other biosignatures in the clouds, or maybe we can find some more evidence for that there is indeed something interesting, possibly alive, happening in the clouds. And this brings me to the end. This work is, of course, a work of many people, and I'm just a spokesperson for them, and nothing what I say here wouldn't be possible without in the involvement of many other people. And I especially would like to thank Professor Jane Greaves and Dr. Anita Richards, the main observers behind the phosphine discovery on Venus, and also my boss, Professor Sarah Ziger. Without her support, none of this would be possible. And also others like spectroscopists Clara Souza Silva and Hideo Sagawa, who were responsible for all this spectroscopy part of the work, and as well as photochemists Paul Rimmer and Sukrit Ranjan, their wonderful work on photochemistry on Venus was actually top notch, and it was an honor. It is an honor to work with them, and also others. And last but not least, my friend Dr. William Baines, who looked at all these various different chemical and physical processes that could produce phosphine on Venus, and essentially that led us to this rather mysterious project. Thank you very much. If you have any questions, of course, let me know, and I believe Zeynep is going to moderate the discussion. So thank you.
Thank you so much. This was delightful.
Thank you. I'm glad. I mean, I'm sorry that I've went like 5 minutes over time, but I hope that this is not a problem. And of course, I mean, if the audience and if you have any questions, then of course, please let me know.
My friend sent me the questions. Now I'm going to read them to you.
Yes.
So the first question is, if there's an organism on Venus, does it necessarily have to be suspended in the atmosphere? If so, how can it stay alive suspended in the air?
Yes, I mean, this is, I've tried to, you see, the one point, that's a very good question, because this is one of the challenges for life in general, how it can sustain itself. We wrote a paper. If you are interested, you can always write to me, and I can guide you to the proper literature. We wrote a hypothesis paper, of course. How would we actually solve if we were a microbe? Yes, in a clouds of Venus, living inside of these sulfuric acid droplets. How would we passively solve the problem of this problem of actually fighting with the gravity, essentially? And this is a very difficult problem. We do not claim that we solved it permanently, but Venus has this very weird, mysterious, stagnant layer right below the clouds. It is a layer that doesn't really move very much, and you can imagine that as the cloud droplets are bumping into each other and they merge and they actually become bigger, they also fall down. Yes. And eventually they reach a temperature when the sulfuric acid evaporates, the water evaporates also, and the contents of these droplets are deposited into this stagnant layer. This stagnant layer is, as the name suggests, stagnant. So as the contents were actually deposited, they are sort of lighter than the initial droplet. So they might persist in this stagnant layer for much longer. Now, this microbe, let's say that it got deposited as a form of a spore, yes, in this stagnant layer, might wait there long enough for a random updraft that can happen. For example, this is still unknown how these updrafts really how often they happen or how efficient they are. We don't know enough about the atmospheric physics of Venus, but there is a possibility of, for example, some move of air that moves this up periodically. So they are brought back to the clouds, and then they can act as a nuclei for new droplets. So they essentially can build a droplet around themselves again. And this is how you can close the cycle, you know? And this is a rather simplified explanation, but we wrote an entire paper about this, how you can actually close the cycle only in the atmosphere, and also how you can replenish your numbers, yes? Because you cannot have a situation when most of the population dies as the process of that falling down onto the surface, but you actually have to replenish it and keep it constant, at least in the clouds. So yeah, that's a very, very good question. Very, very difficult problem to solve. But you see, life is ingenious. Yes, if we look at life around us, then some of the solutions that life found to almost unsolvable problems are just amazing. It's very difficult to predict biology, and it's very difficult to predict what we are going to see if we ever find life elsewhere. Yes.
Thank you so much. And the other question is, do you think that we should focus on Venus? Does Venus give hope about the life? Should we do researches like we did in Mars?
Oh, by all means, I do not want to sound like that like we should suddenly like abandon other planets and just jump on Venus and just study this planet. What our research tries to point out is that our solar system might be much more interesting astrobiologically than we before thought. It might be because Venus was, you know, when people initially during the Cold War, they were exploring Venus quite nicely because quite efficiently, because nobody knew what the planet was. And then there was this sort of, forgive me for this word, downer, when everybody saw, oh, it's a hellhole. It's just a hellhole. Their surface is so unbelievably hot. Nothing is going to happen there. So okay, so the enthusiasm for this planet sort of died down a little bit. And the recent work, and in my talk, I just wanted to point out that this phosphine discovery, it's not on its own. It's just part of the other hints that indeed something happens in the Venusian clouds, that it's really weird and it's really unexpected. So that could point to the life as a hypothesis. But of course, we shouldn't favor this hypothesis over this chemical hypothesis as well. This does not mean that we should just, for example, abandon Mars or abandon the icy moons in Europa or Enceladus and so on, or even Titan. That is a very, very interesting world, very different than anything else. It just means that we shouldn't ignore Venus and its astrobiological potential, because it might be that this planet is maybe dying, but it might not be dead, you know, not at least yet.
Thank you so much. The other question is it possible to phosphine has a brand new chemical process to form different than we know? Absolutely,
absolutely, and we really tried to emphasize that in the paper. That, you see, I know that, of course, when you talk to the media, people are always going to jump to the most exciting, most exciting possibility. Because, look, there might be some unknown photochemical process on Venus that produces phosphine. That's the first headline. Or do you rather like the headline, oh, there might be life that produces phosphine on the clouds of Venus? Which headline would you like to have? Yes, that's obvious. And so, but what in our papers, we really emphasize that the Venusian cloud conditions are not really known, not fully understood. And there might be some processes, chemical processes, that are actually responsible for the production of phosphine that we just simply don't know. What if I were to bet that for some sort of chemical process that produces phosphine in the clouds, then it would probably involve to some degree, this phosphorus acid. When I showed this one reactions that you can produce this phosphorus acid as an intermediate and then essentially produce phosphine later on and have sort of like this pathway of it. None of those sort of obvious phosphorus acid reactions produce phosphine, yes? But there might be some weird, for example, and I'm making stuff up now, because we don't know what process produces phosphine, so I'm making some process right now. What if we have some photochemical process that produces this phosphorus acid, for example, yes, that we don't know of, and it somehow produces it in the context of this, sulfuric acid as well, and, weird surface chemistry of the droplets and God knows what. Then what if it, for example, then falls down somehow and then it decomposes and this produces this phosphine up, and then phosphine goes up somehow. But the problem is that it's all difficult, and it's, of course, a speculation. And that's a very important point. On the Earth, phosphine is produced only by biology. So that's why not making this hypothesis about biological possibility is also not honest, really, because we have all these other different mysteries of Venus, and that point to some sort of weird chemistry or maybe even biology. Even the modeling for Professor Michael Way suggests that Venus might have been like Earth for billions of years. And suddenly we have this phosphine, which completely doesn't fit there, completely. And so, yeah, absolutely. Answering your question very, very shortly, there might be a chemical process. Well, it might even be likely that there is, because we don't know everything about the planet. That's why we have to also study this. And I often say that the exploration of Venus can happen on Earth, because we can actually try to come up with some sort of chemical reactions and test them in the lab in the quasi-Venusian-like environment to check if, for example, phosphine is produced in this. But we have to be careful because phosphine is a poison. So if we actually prove that this chemical reaction, we should be ready to be protected. I don't know. Yeah.
Yes. Thank you. And the other question is, if there used to be oceans on the surface of Venus, what could have caused them to disappear?
Very good question. And the honest answer is we don't really know. But so what happened, if modeling of Professor Michael Way is correct, what happened around 700 million years to Venus that it actually put it on this track to complete change? Yes. And what we think at the current stage is that there was some sort of geological cataclysm, like unbelievably massive volcanic eruption. And we can colloquially say that, let's imagine that all volcanoes on the planet erupted at the same time. Then there was a lot of carbon dioxide that got released to the atmosphere. And what we think is that this carbon dioxide, after these eruptions happened, paradoxically, Venus then started cooling too fast. And this carbon dioxide didn't really get reabsorbed by the surface fast enough, and it actually stayed in the atmosphere for too long, or actually couldn't be taken down. Now, this sort of put Venus on this spiral of heating up, then the oceans evaporate. Then you can imagine that the oceans, when they evaporated, that heated up the planet even more, and then eventually the water even got lost to space because it got photochemically destroyed, and hydrogen escaped to space, while the water essentially disappeared. There's a very important point to make, which I didn't really emphasize in the discussion, in the presentation, that Venus is famously hydrogen scarce. There is very little hydrogen, like as an element. Yes, like hydrogen in the atmosphere or in the planet in general, and that's very weird. That's because Venus actually lost all its oceans. So imagine now that you are producing phosphine in an environment which is super spectacular, which you need 3 atoms of hydrogen in an environment which is hydrogen scarce. It's another mystery, and that's why it is so difficult to produce.
I see. Thank you. And the other question is there any organic molecule that can exist without life? If there is, how we call them?
Oh, organic molecule that can exist without life.
Yes.
Okay. So organic molecules. So the name organic molecules comes from the point of view that they were initially large complex carbon molecules that were isolated from living organisms. But of course, organic chemistry, the carbon chemistry, can form also without life. And that's actually an important question in the search for biosignatures. That biosignature is some sign of life. Can you honestly exclude any non-biological processes to actually, because exclusion of a process, this is what is quite important to make to this point now also. We exclude all those processes, but exclusion of the process doesn't mean that we prove another. Yes, that's a very important distinction to make. If we exclude all the non-biological processes, it doesn't mean that we prove life. And this is the problem also with organic molecules, and what the viewer asks about is that yes, there are processes that are capable of forming of various organic molecules. There are all kinds of organic molecules present in the interstellar medium as well, or on meteorites or other places. They were presumably formed by some non-biological process. Now we can say, so there are processes like that. We can say that the more complex the molecule is, the less likely it is to be made by some non-biological process. Because for example, if you suddenly found a large polymer or a molecule of some organic complex alkaloid, yes, from some plant somewhere in the interstellar medium, you would be puzzled to the extreme, because you would not expect random chemistry to come up with such complex molecules just by chance. So it's so the more complex the molecule is, the less likely it is a non-biological one.
Okay, thank you. And the other question is, we can only try to understand the possible life on Venus based on our understanding of life. However, if the life form there is very different, would it be possible to take samples and examine them?
I hope, well, first of all, if life exists there, it's a highly hypothetical one, the question, of course. But the point is, yes, that's why I wanted to emphasize this point in my presentation, that the ecological aspect of the clouds of Venus is so different that it forces this life to be different than what we have here on Earth. But we have to be aware that we have to always, when we are astrobiologists, we have to have open mind, because we have only one example of life here on Earth. And everybody here is related, everybody uses the same chemistry, and everybody is essentially the same in terms of the cellular machinery. But is this the only way you can build life? And we don't know that. Honestly, this is the honest answer. This is one of my main research topics. I really like to think about it, and I really like to solve this question. Does life really have a choice with respect to its chemistry? For example, speaking philosophically, if you started life on Earth from scratch, like 4.5 billion years ago, to transfer and start everything from scratch again, would you arrive at the same conclusion? Would you also have DNA? Would you also have proteins? Would you have also the same biochemical pathways that you have now? We don't know. And that's why, when people say, that's why I wanted to emphasize the question of the reaction with the sugar and so on. Because obviously you are not going to build this life there based on these sugars, and you are not going to transfer just Earth life and just like highs there. It's impossible. Yes, because you have to. Because this is the funny thing. You could build biochemistry. Oh, we have to talk a little bit about that. Can you originate life in some other conditions than water? We don't know that.
We don't know, right?
Water is fantastic solvent, yes? But what life really needs is some sort of liquid. It needs liquids to actually get its reactions, to bring molecules together and so on efficiently, also keep this contained. And sulfuric acid is a liquid, yes? And it's there in the clouds and the droplets, So yeah, well, that's why this phosphine and this other hypothesis, these other weird things about Venus are so cool, because everything, all those mysteries happens in this cloud layer when there is liquid and the temperature is not too high. Yes, the mysterious unknown absorber is in the top layer of the clouds, and the phosphine is in the top layer of the clouds. So it's really, and the clouds are made of liquid droplets. Well, okay. Now, can you originate life in sulfuric acid, for example? No, probably not. And you see, this is me being skeptical, because probably not, because acid is not very good when it comes to producing these precursors for life. Water is better. So there is a chicken and egg paradox, that probably you can, in principle, build a biochemistry in sulfuric acid, some stable polymers and, have everything running around. It would be completely different, yes, than what we have here on Earth. But you probably cannot build these building blocks so you can build this biochemistry. So it's a weird thing. So now the question is different. What if this life on Venus was actually water-based, and then it evolved, it adapted to these sulfuric acid conditions in the clouds? And now this is we don't know the answer, of course, but we shouldn't be ashamed of asking this question. Can we imagine that life can adapt to conditions that it essentially that is essentially is capable over hundreds of millions of years as the environment on Venus changed gradually. Can it actually change its solvent? Can it actually adapt its entire biochemistry to this sulfuric acid somehow and use it to a greater degree? I know that I probably will get a lot of flack for even stating this out loud, but why not answer this question? Why not actually ask it, and why not think about it? If you had hundreds of millions of years and gradual acidification of the environment, and you eventually ended up in an environment that has 85% of sulfuric acid, can you actually somehow hugely tweak your eventually over hundreds of million years, tweak your biochemistry so you actually not only survive in it, but you need it? Think about it this way. If we were life that doesn't use oxygen, and you are intelligent, and we look if it is even possible, let's say, but hypothetically, and we looked at Earth, we found Earth, and we saw oxygen in the planet, in the atmosphere of this weird planet, this weird exoplanet that we call the Earth. We would not say that this is life. We would not say that life is possible in an oxygen-rich environment. What we will say is that oxygen is such a reactive molecule that you produce ozone and other reactive oxygen species that destroy absolutely our organic chemistry. And what we also would probably arrive at is that, oh my God, we discovered on Earth, on their Earth, we discovered on their planet that there is a special flammable chemistry in the high oxygen temperature, high oxygen concentrations. They call it fire, let's say. Oh my God, organic matter burns in oxygen. It is impossible. Yes, it is impossible. So we will arrive at the conclusion that Earth is an impossible place for life to exist. This was like that 2.5 billion years ago, when life was essentially non-oxygen. It was the greatest poison to all life on Earth. And then we adapted to it first, and then we started requiring it. What if an analogous situation we have on Venus? Just as a speculative thing to think about.
Yes, thank you so much. And the last question is, what do you suggest for someone who is interested in astrobiology?
What do I suggest?
Yes.
Read a lot. Because, you know, one thing is that I'm a biologist by training. And don't be ashamed of it. You see, don't be ashamed to call yourself astrobiologist. Don't be ashamed that you are thinking about these things, that you are asking these highly hypothetical questions, because there will be a moment in the future when this is going to be a reality. Yes? Everyday life. What I suggest is that astrobiology is very interdisciplinary field. It essentially welcomes absolutely everybody. This doesn't matter if you are a mathematician, physicist, biologist, chemist, geologist, astronomer, everybody. Because this field, to be successful in this field, to answer this question, are we alone in the universe? We need all of those sciences to come together. All of them. We cannot answer it. Okay, you know what? Let's answer the question of, are we alone in the universe on the basis of mathematics alone? We wouldn't be able to do that. So all of those people who study all of those different sciences can contribute to astrobiology. So it essentially doesn't even, and I risk using this word, doesn't even matter what you study, because there is always an astrobiological question that you can ask, which is within the realms of your favorite science that you study. So that's my answer, and that's my advice. Study a lot, read a lot of things outside of your branch of study. But the great thing about astrobiology is that essentially your previous choices in life do not close the possibility of you becoming an astrobiologist in the future. Because I was an X-ray crystallographer, I was studying the proteins, I was studying the structures of proteins, for example, for my PhD. And now I look for life on other planets.
Actually, we saw it in here too. We had a philosophy and linguistic professor to talk about astrobiology?
Yes, of course. Because it's such a broad discipline. It's such a broad discipline. And it's also a discipline that allows you to dream, to imagine things, you know. And I think that people need that also, you know, to think a little bit outside of, you know, the realm of, and you shouldn't be ashamed of that as well.
Okay, thank you so much. This was all of the questions. Thank you so much for being here today again.
My pleasure. My pleasure. It was a great meeting, and I really hope that the audience found it interesting and engaging, and I look forward to. I mean, who knows? I mean, you do this once a year, so who knows? And I look forward to further meetings that you do. Thank you very much.
Thank you so much.
Bye bye.
So today was the last day of Astrobiology Live Presentation series, and I would like to thank all of our precious academics who accepted to join us here, and I would like to thank all of you for making this possible. And last, I would like to thank all of my friends. You saw only a couple of them here, but there's a huge team behind this, and I want to thank all of them for all of their hard work, passion, and effort. And this was the end of this year's event. Till next year, you can follow us from our social media accounts and give us any comments and ask any questions. I hope to see you next year, hopefully in a face-to-face event. Thank you so much again. Stay safe and stay healthy.